Okay, so this is going to be 16.10. This is the last piece of new information before your test on Thursday. Very small little piece, but very important as well, because a lot of what this section or this part of the chapter is about is acid and base strength, right? How we measure acid and base strength, like pH and Ka, Kb, etc. And now we're going to look at how the actual chemical structure of the acid can affect its strength. Now, I want you to think of an acid like this. I'm just going to call this X, right? And in order for this to pop off, this H plus, to go to X minus, what I really want is for all my electron density to lie around X. And the more I pull, the more electronegative this is, and this could be a group of atoms, or it can be one element, one atom. The more I pull the electrons in this direction, the easier it is going to be to pop this off. Because remember, this is a bare nucleus with just a proton in it, and all the electrons are over here. So the more electronegative this is, the easier this is going to be to pull off. So the strength, now what we want to look at is strength of the HX bond. Now we're going to kind of focus on vertical and horizontal on the periodic table, and then we're going to combine the two and look at a little bit of both. Now remember that if I have an element attached to H, so let's look at one element first, and then we'll look at groups of elements. As I go, the strength of HX tends to decrease as the element of X increases in size. So this is going to be down, so vertical, down the group of the periodic table. Let's look at the halogens first. As I go down, I go from having this, which might be HF, to this would be HI. And what happens is the distance between the two centers is going up as I go down, and the coercive strength of the bond is going to decrease because it's harder for these electrons in this nucleus to find each other. It's a longer bond. It's more diffuse. The higher the bond energy, another way we can do that, the more difficult it is for that bond to be broken. So if you noticed, when I'm here at HF, I'm getting a periodic table over here real quick so we can look at that, right? So as I'm over here at HF, remember this is the most electronegative atom. It's also the smallest one. As I go down, the elements get bigger and bigger. So the bond strength is very high here between HF and low here. And you can see that with the numbers, the difference. So what happens is, if in order to cause this to become an acid, I throw this in water, then the stronger this bond, since HX must break, the stronger HX bond is, the weaker the acid. And remember, this makes sense because remember that all of these, HCl, HBr, and HI, these are strongs. HF is a weak acid. So that alone shows you that this bond is much harder to break than all of these, and that makes this completely in a separate category. These are strong acids, and that is weak. Okay. So this is vertical on the periodic table. All right, now let's move across the period. Remember that electronegativity tends to increase. So remember, as we go down the group, we really talk about size and atomic radius. So the atomic radius is increasing as we go down. Therefore, the bond is lengthening and the bond energy is going down. As we go across the period, however, the electronegativity of the elements is increasing. Okay? As we move from the top to the bottom down a group, electronegativity tends to decrease vertically. Okay, so this is across the period, this is down the group. Now, which bond then is going to be more polar, HO or HF? Well, HF is most polar because HF, the hydrogen is about 2.1. I think this one is 4. HO, this is about 2.1. I think this is around 3.5. So what that means is that this is much more electronegative. This bond is much more polar. So HF is more polar. Therefore, it is more likely to give up H+. Another way to look at this is that what this means is that in this bond that's being shared, most of the electrons are sitting on fluorine because its electronegativity is high. In this case, I still have most of it here, but the difference between them is not as much. So again, if the electron density is sitting on the fluorine, it's not on the hydrogen, that allows H+ to pop off more easily. So HF, therefore, HF is strongest. Okay. The more electrons I pull away, the more I'm going to see acidic character. All right. Now, what if I add other groups or other atoms onto this bond? HOCl and HOI. All right. Now, this one, chlorine, remember, is up here. It's going to be more electronegative than this. So I'm going to have a bigger pull here than I do here. And because of that, this OCl is the stronger acid. So I'm going to kind of summarize. What have we talked about? The first thing we talked about up here is the lower the bond energy, the weaker the acid. Oh, stronger, sorry. The stronger the acid. So when we look up here, these are all very strong acids. Notice their bond energies are very low, and this one is high. That is a weaker. So the lower the bond energy, the stronger the acid, because it's easier for that hydrogen to pop off. The more polarizable the HX bond, the stronger the acid. So as I move electrons in that direction, this is going to be the weaker acid. As I move electrons more in this direction as compared to this one, so this is going to be the stronger one, and in this case, this is going to be the stronger acid. Okay, now last but not least, we're going to look at a couple other little things that help us determine acidity and basicity. What if I start adding multiple atoms? What if, and I'm not going to draw this as a Lewis structure, I'm just drawing it like this as opposed to this. Now again, I've got my electrons going a lot farther more this way because these are all electronegative, and a little bit this way. Therefore, this is the stronger acid. as electronegativity increases with increasing number of oxygens. And then last but not least, we want to look at the carboxyl group. Remember when we did resonance? When I take a proton off of the carboxyl group, I can draw two resonance structures, if you remember. Like that. Now, what this does is it stabilizes. This is our third criteria of how we determine the acidity and basicity of different chemical structures. Stability of anion. The more stable the anion, the stronger the acid. So if pulling off the proton gives me something really lower in energy like these, because these do lower the energy of the overall anion, then that proton is more likely to come off. And so this is a little bit more stable. So in reviewing, we learned 1, the lower the bond energy, the stronger the acid, right? Because it's easier to break that bond. 2, the more polarizable the bond. So if there's a more electronegative atom next to the proton, the more polarizable it is, or the greater the difference between these two, the stronger the acid. And then last but not least is the more stable the anion, the stronger the acid. So those are the few things that tell us a little bit about stability and acid strength.